Hidden inside a wobble in starlight too small to notice with the naked eye, there is a trace of gas leaking off a planet that has no business still having anything left to leak. But that leak has been happening, on and off, for 3 billion years. And when scientists finally pinned it down and ran the numbers on the star it is orbiting, they realized the planet should have lost this fight a long time ago. Its catalog name is LHS 1140b, and the people who found it are still working out how it won. To understand why a little bit of leaking gas counts as a scientific emergency, you have to understand what red dwarf stars actually do to the planets huddled close around them. Red dwarfs are the runts of the stellar world, smaller than our sun, cooler than our sun, dim enough that a planet has to orbit uncomfortably close just to feel any warmth at all. That part sounds gentle. It is not. Young red dwarfs spend their early lives throwing out X-rays and ultraviolet radiation completely out of proportion to their size, and unlike our sun, which calmed down billions of years ago, some of them keep throwing tantrums for a very long time. A planet parked close enough to stay warm is also parked close enough to get scoured. Hydrogen goes first, because hydrogen is light, and radiation flings it away easily. Then the heavier gases start to follow. Model after model has said the same thing for years. Rocky planets around aggressive little stars like this should end up bare. Scorched rock, no sky, no chemistry, nothing left to measure. In 2017, two researchers named Kevin Zonla and David Catling turned that assumption into an actual line you could draw. They took every planet and moon we had good data on and plotted two numbers against each other: how much radiation each world had absorbed over its lifetime, and how easily its gravity let gas escape into space. When the dust settled, the plot split almost perfectly into two camps: airless worlds on one side, worlds with atmospheres on the other. Almost nothing sat in the middle. They called it the cosmic shoreline, and it has been the working rulebook ever since for predicting which planets keep their air and which ones don't. Mercury and our own moon, both stripped bare, landed exactly where the model said they should. Venus, Earth, and Titan, all still wrapped in thick atmospheres, landed just as cleanly on the other side. The line worked, which made it a problem for any planet that landed close enough to the middle to leave the outcome genuinely in doubt. LHS 1140b was discovered that same year, 2017, by a researcher named Jason Dittman, using a network of small robotic telescopes called the Meerth Project, built specifically to watch red dwarfs for exactly this kind of catch. The planet turned out to be a rocky super-Earth, about 5.5 times Earth's mass, 1 7/10 times its width, circling its star every 24 7/10 days at a distance of 48 light-years from us, in the constellation Cetus, close enough to its dim red star to sit inside the habitable zone, close enough to that same star to sit right on the edge of Zonla and Catling's shoreline, in the gap where nobody could say with confidence which way it would fall. That uncertainty sat there, unresolved, for years, because confirming an atmosphere on a rocky planet is already brutally difficult. Confirming one on a planet 48 light-years away, using nothing but the light that happens to reach us, is close to the edge of what current instruments can do at all. Here is how they finally did it. Nobody has a spacecraft anywhere near LHS 1140, and nobody will for a very long time. So instead of visiting the planet, researchers waited for it to cross directly in front of its star, and measured exactly how the starlight changed as it grazed the thin envelope of gas wrapped around the planet's edge. Every element absorbs light differently. Split that starlight apart finely enough, and the gas announces its own ingredients. The instrument built for this particular job is called WINERED, a warm infrared spectrograph mounted on the Magellan clay telescope in Chile, tuned to catch one very specific fingerprint: helium bleeding off the top of a planet's atmosphere as it transits. Helium matters here because it is heavier than hydrogen. If a planet has already lost its hydrogen and there is still helium escaping, that helium is the last visible chapter of a much longer story about everything the planet lost before anyone was watching. In 2024, the sky handed researchers a rare gift. LHS 1140b and its smaller sibling planet, LHS 1140c, transited their star close together, giving scientists a chance to measure both at once and compare them directly. The team, led by Colin Cherubim, a NASA Hubble Fellow at Harvard Center for Astrophysics, who had just finished his doctorate in Earth and planetary sciences, pointed WINERED at the pair and got a result nobody had ever gotten before. As Cherubim put it afterward, "This is the first time anyone has found an atmosphere on a rocky planet in the habitable zone," a sentence that took an enormous amount of searching to earn. Cherubim's doctoral advisors at Harvard, Robin Wordsworth and David Charbonneau, had spent years chasing versions of this exact question, and the result finally landed in the journal Science this July. Here is where it gets strange. When the team went back to check the signal again in 2025, expecting confirmation, the helium simply was not there. Gone. Not a weaker version of the same reading, not noise, nothing at all where a clear signal had been the year before. That is not a contradiction in the data. It is a clue. It means the atmosphere is not bleeding away in some slow, steady drip that would show up the same way every time you looked. It is losing gas in bursts, most likely tied to spikes in the star's own radiation, meaning some years this planet is actively hemorrhaging its sky into space, and other years, for reasons nobody has nailed down yet, it simply is not. A planet that flickers between visibly losing its atmosphere and looking calm is not a planet quietly holding steady. It is a planet caught mid-fight, and the fight has apparently been going on since before there was multicellular life anywhere in our own solar system. Why helium and not something lighter? Cherubim's own explanation is almost embarrassingly simple. Hydrogen is the lightest element there is, and it is the easiest thing in existence to blow off into space. This planet's upper atmosphere is already helium-dominated, hydrogen-poor, which means the hydrogen is largely gone, stripped away over billions of years, while the heavier helium underneath has held on just long enough to still be there when someone finally pointed the right instrument at it. Researchers suspect water may be sitting even further down, sealed beneath the helium layer, hidden from exactly the radiation that keeps stripping everything above it. If the planet had lost everything at once, none of this would be sitting here to measure. What the data is actually showing is a layered, ongoing negotiation between a star trying to strip a planet bare and a planet giving up only what it has to. And then there is the sibling, LHS 1140c, smaller than B, sitting closer to the star, catching even more radiation, showed nothing. No atmospheric signal at all in the exact same dataset from the exact same star, same system, similar rock, and one planet came back essentially naked, while the other is still holding measurable gas after 3 billion years. Researchers now treat LHS 1140c as sitting cleanly on the dry side of the cosmic shoreline, exactly where the model predicted. LHS 1140b sits right on the edge of the wet side, by a margin thinner than anyone expected to find. Picture standing on it anyway, because the picture is worth holding on to. 42% of the sunlight Earth receives reaches this planet's surface, so the sky sits in a permanent dim red twilight, lit by a star that looks more like a dying ember than anything we would call a sun. Underfoot, dense rock built to carry nearly 6 times Earth's mass inside a world less than twice as wide. Overhead, an atmosphere far thinner than ours, patched together out of leftover helium and whatever water is sealed beneath it, thinning further every time the star throws another burst of radiation across the system. Somewhere nearby in that same system, on its own tighter orbit, sits LHS 1140c, stripped completely bare, quiet proof of exactly what this same star can do to a planet that cannot fight back. Sit with the number for a second, because 3 billion years is not a casual span to attach to something this fragile. Earth itself is only about 4.5 billion years old, and life did not appear here until somewhere around 3.5 to 4 billion years ago, back when our own atmosphere was still a toxic, oxygen-free haze that would have killed almost everything alive today. LHS 1140b has apparently been holding some version of an atmosphere for a stretch of time close to the entire gap between Earth's formation and the first microbes showing up in its oceans. That is not a planet that got lucky once. That is a planet that has been grinding out this argument for the better part of the universe's working lifetime. Which raises an uncomfortable question about scale. Red dwarfs make up something like 3/4 of every star in the Milky Way. If the shoreline model is right for most of them, and it generally is, most of the galaxy's most common stars are circled by scorched, airless rock. That has been the working assumption behind an enormous amount of pessimism about how common breathable atmospheres actually are out there. LHS 1140b does not overturn that assumption. It puts a crack in it. If one rocky planet, sitting inside the habitable zone of an aggressive little star, can hold on this long, the shoreline is not a wall with nothing on the far side. It is closer to an actual coastline, uneven, with pockets where a planet can apparently dig in and hold ground longer than the model ever predicted. Cherubim framed it around 3 separate conditions a planet needs before anyone will call it a real habitability candidate: the right size, the right distance from its star, and an atmosphere. In his words, with this discovery, we now know LHS 1140b has all 3 of those things, which is really exciting. Researchers had confirmed the first 2 on plenty of worlds already. Nobody had confirmed the third, on a genuinely rocky planet, inside a genuine habitable zone, until this one. There is a second search running in parallel right now that makes this result even more interesting. The James Webb Space Telescope has spent years chasing a similar signal around a completely different planet, TRAPPIST-1e, one of 7 Earth-sized worlds circling another small red star. Webb has logged nearly 20 separate transits of that planet so far, because the signal it is hunting for is faint enough to hide inside ordinary noise unless you stack years of repeated passes on top of each other. LHS 1140b's confirmation did not need anywhere near that much patience. It came from a ground-based spectrograph in Chile, watching one rare alignment that will not repeat again for a while, and it came back strong enough to stand on its own. 2 teams, 2 instruments, 2 completely different strategies, chasing the same basic question from opposite directions. For now, LHS 1140b is the one that got there first. Somewhere out past the edge of what the model said should be possible, there is a small, rocky world still holding onto its own sky. What do you think is actually keeping it there? What do you think is really going on out there? Leave it in the comments and stay with us here, because today, the space world just got stranger. Thank you for watching. See you in the next one.